Good day. So, today and in the next lecture we will be talking about switches. Switches are the most important part of computer networks, and we will just look into some aspects of the different types of switches. So, first in this lecture we will start with the kind of switches which are used in telecom networks. Okay. And then there is a special version of these which we will cover in a later lecture, and then in the next lecture we will be talking about packet switches which are closer to the heart of data networks. So, we talk about switches. First thing is, why do we need switches? Well, the problem is that each user can potentially call any other user, as we have seen in telephone networks. So, and we cannot have direct lines, we cannot have order n square kind of lines. So, every user is connected to essentially a switch in the switching office, and switches establish temporary circuits. That means, they establish a temporary connection between the caller and the callee at the switching station, and switching systems comes in two parts. One is the switch and the other is the switch controller. So, we will just have a look at this switch and the switch controller. As you remember from our discussion about telecom networks, that people want to talk to other subscribers who are in maybe in a different location under a different switching station. So, the switching stations have to connect amongst themselves. So, for making this connection through the signaling that we talked about, there is a control plane over here. So, in the control plane they are basically, you may think of them as some kind of computers which are capable of giving sending some kind of signals or instructions to the individual switches. So, in the control plane we set up the path, and there is a corresponding signal from the controller to the corresponding switch for setting up a particular circuit or a particular connection, so that an end to end connection from one user to the other is set up. So, this control plane is sort of at an overlay network over this actual switch, and once the connection is set up, naturally all the call and all the signals etc. flow in this plane. There is a network device called routers, and there is this thing called routing, and which is very close to switching. Only thing is that in a routing we decide about long range paths. Okay. That means, the essentially, if you remember from our discussion about the 7 layer OSI protocols, you remember that there was a network layer, and the job of, and the router is a device in the network layer whose job is to find out that in order to reach the ultimate destination station, okay, what is the local link that I have to take here, alright. So, that is the job of a router, whereas for a switch it is slightly simpler, it is a strictly local decision. For the router there is a global implication that what is the local link on the output side that I must take for an input line, a signal coming through an input line to a particular destination, what is the local link that I must take, so that I will finally, through all these connections through various other routers, I will finally reach my destination. Whereas for a switch the job is a little simpler, in the sense that it is just that for the incoming link, what is the, I have to, the signal is coming from one incoming link and it is going to go out to a particular outgoing link which is known at the switch. So, how to set up the connection, and of course, actually a router is a switch with some added on functionality, alright. So, many connections will need paths through more than one switch. So, that is when we require routing. Static routing uses the same approach all the time, that means a same destination is routed through the same path all the time. and dynamic routing may allow changes in routing depending on traffic, that means in some part of the network may be congested. So, it might want to avoid that part and go to the same destination through some other part, that is dynamic routing. And as we have seen in at least in telephone networks, because of the way we distribute the telephone numbers to subscribers, it is easy to route. You can look at those incoming digits and just decide on the route. And switching is the local connectivity between input and output lines. Now, just some basic concepts and terminology. One is the transfer medium. Okay, transfer medium in a switch, it can be buses that deliver cells. Okay, buses means electronic buses through which you can send a stream of cells. Queues are memory locations that temporarily store cells. As we will see that switches often require some queues. The queues may be on the input side, the queues may be on the output side, queues may be at various places. So, we will look at all these different cases, but these are temporary memory locations where we temporarily store some cell till we know what to do with it, or we can forward it to its destination. The switching element is the building block for the switch. So, a switching element, what it would do is that I mean either you see a switch may be either on or off, or in so if it is on, that connection is there, or if it is off, the connection is not there. Sometimes the switch is like this, that at a particular point a switch may connect either to one point or to another point, okay, either to one point or to another point. So, switch is just that simple element, and in a big switch we have lot of these switching elements. Okay. So, and these switching elements, they form a so called switching fabric, that means the shape of the switch, I mean how the switches are organized, so that all incoming calls can be handled. There is a term called blocking and non-blocking. Okay. Blocking means a network is unable to connect stations because all paths are in use. A blocking network allows this. This is used in voice systems, and the main reason is that we have short duration calls. The point is this, that there are so many subscribers, okay, maybe thousands of subscribers. If we want to provide or the switching capability for, so that to the maximum possible extent, that means if everybody is busy talking to somebody or the other, that means if every subscriber is using this, then we will, I mean if we try to provision our equipment based on this assumption that everybody may be talking to everybody at the same time, then the switch will become very big, okay, and it will become very expensive. So, what the telephone people have done is that they have made extensive study of how many people are likely to talk during some particular time of the day. Especially Bell Labs in the USA, they were pioneers. There was a very giant telephone company at one point of time, the largest at one point of time. Later on it was broken up, etc. Anyway, so during the early part of the maybe 1940s and 50s and all, they made very extensive study about people's calling habits. So, they found out that during the busy hour, okay, maybe the peak hour, when all the offices are open, etc., how many people out of a subscriber base of so much are likely to call. Okay, that is one kind of statistics they collected. And the other kind of statistics they collected is that once a person starts talking, what is the distribution of the call duration, okay, for how long is this particular subscriber likely to hold on to that line. Okay. So, they found the statistical distribution, they got a very nice fit, etc., and based on that they decided that, okay, if I provision just this much in terms of our switching elements and switching capacity, then almost all the time everybody will be able to get the service, but exceptions may occur. That means at some particular time, because since this is based on some statistical study, at some particular point of time it may so happen that the number of subscribers who wanted to speak is just larger than the overall switching capacity that you have. In that case, some of the calls will be blocked. Okay. So, so that some of the calls may be blocked. So, I am just giving you, I mean talking in terms of switching capacity, this kind of blocking may occur elsewhere in the network also. But anyway, so we provision based on some statistical averages, but at exceptional times for short durations of time we may have to block some of the calls, because we do not have the capacity to handle so many calls at the same time. So, that is a situation where it is blocking, and what people try to do is that they try to calculate the blocking probability. Alright, what is the probability of blocking? Maybe 1%, 2% or 5%, 5% is quite a high. Okay, nowadays people do not even like that. So, what is the that is the blocking probability that we wish to achieve by provisioning this much for so many subscribers. Okay. Non-blocking, of course, the other one which permits all stations to connect in pairs at once. Okay. This may be used for some data connection where blocking is not allowed or blocking is not acceptable under any circumstances, etc. Naturally, if you want to make it fully non-blocking, that solution would be more expensive than if you allow a limited amount of blocking. Of course, if a high degree of blocking would not be acceptable to the users at all. So, now let us take, there are various kinds of switches, okay, and I am trying to present here a taxonomy of different type of switches, not that all actual switches neatly fit into the boxes. Some of them take some portions of this, and some there is some kind of a hybrid or mixture, but this is one way in which the different type of switches can be classified. Okay. So, we have space division switching. So, we will look at some space division switches. There are time division switching. Just as if you remember, like in multiplexing, we have time division multiplexing, frequency division multiplexing. Here we have space division switching and time division switching. Time division switching is very close to time division multiplexing, as we will see. Now, in space division switches may be a single stage or it may be multi-stage. In single stage we have switching matrix, then we have a knockout network, shuffle exchange networks. In multi-stage it may be a single path or multi-path, like delta networks or Banyan networks, sorting networks, etc. In time division switches we have shared memory and shared medium. In shared memory could be a central memory, or shared medium could be a bus or a ring, etc. So, these are different types of switches. So, we will not have the time to look at all these in detail. So, we will just look at some of the very common type of switches that are used. Okay. So, let us first talk about space division switching. It was developed chiefly for analog environment, separate. So, and why do we call it space division? Because the different calls go through separate physical paths. So, that is why they are called space division switches. Unlike time division, where different calls may be going through the same physical path at different time slots. So, we will come to that when we discuss time division switching, but in space division switching different calls go through separate physical paths. And the simplest of space division switches is a crossbar switch. Okay. So, number of cross points grows as the square of number of stations, as we will see. Loss of cross point prevents connection if a particular cross point becomes bad. It is an inefficient use of cross points, and all stations connected, only a few cross points are actually in use. This is fully non-blocking. Let us first have a quick look at a crossbar switch. So, a crossbar switch is very simple. I mean, what do you have in a switch? In a switch you have n input lines coming on from one side and n output lines. You have to connect some of the line. Let us say I want to connect this particular line, this particular input line to, let us say, this particular output line. Okay. No, sorry, not this, maybe this. Okay. So, the fourth input line I want to connect to the fifth output line. So, what I want is that I want this particular switch to be on and other switches off. So, if this particular switch is on, then there is a connection between this line and this line. So, I have a direct physical path between the fourth input line and the fifth output line. Okay. And each of these crosses that you see is a single switching element, and as you can see, since there are n lines, if there are n lines on this side and n line on the output side, so we have n square kind of switches, n square switching elements, which actually is quite a lot. Okay. So, if you go back, the number of cross points grows as the square of the number of stations. Okay. So, that is one point, that it grows as the square of number of stations. And if a particular, let us say that particular switch which is at the crossing point between the say fourth input line and the fifth output line, if that particular switching element somehow has gone bad, then 4 and 5 cannot talk to each other ever. Okay. So, that is again another drawback of this kind of switch. And of course, it is an inefficient use of cross point. At every cross point we have a switch, all stations are connected, but only a few cross points are actually in use. Okay. At most, of course, only n by 2 cross points can actually be in use, whereas we are using n square cross points, which is really a poor utilization of the switches. Of course, one good thing about it is that this kind of switch or this particular version of the switch is totally non-blocking. That means all pairs of subscribers can talk to each other at the same time. Other points about the crossbar switch is that in its simplest form, n input line, n output line, hence n square electronic switches. If all lines are full duplex, that means all lines allow communication in both the direction, then we require only half the number of switches. Okay. First of all, we possibly do not require the diagonal switches, the switches which are in the diagonal. I do not want to talk to myself, and the other thing is that only either a top half or the bottom half of the switches, top half means top half above the principal diagonal or the bottom half below the principal diagonal, that triangle. So, only those switches are required. So, in general n square by 2 switches would be required if you have full duplex lines. And the other problem about the crossbar switches is that apart from the number of switches, the number of IO pins is also a problem. Okay. If you want to make let us say a 1000 by 1000 line switches, 1000 subscribers suppose you have. So, you may have 1000 incoming lines, 1000 outgoing lines. Okay. But how do you put all these 1000 plus 1000, 2000 pins, okay, on the whatever chip you try to make. So, that also becomes an issue and it becomes a problem. So, this is now of course, I mean people have gone to more sophisticated design for switches and they are classified in various ways, one through input queuing, output queuing or central queuing. We will look at this one by one later on. Let us look another kind of space division switches known as knockout switches, which was introduced in 1987 by AT&T Bell Labs. Essentially, we use output queuing over here. We will look at output queuing and the issues in details later on. So, there are actually the point is that if the switch is trying to pump in more number of bits or more number of bits to a particular output line than that output line can handle, then these bits either you have to drop them or you have to store them somewhere, maybe in a queue. So, and that queue is associated with the output port. So, that is what we mean by output queuing. So, n inlets and n outlets operate at the same speed. Transfer medium consists of n broadcast buses, one for each inlet, n bus interface units, one for each outlet, each takes input from all the broadcast buses, each delivers output to its own outlet. So, just let us have a look at the figure. So, we have the n input lines on one side. Okay. So, these are the n input lines. So, call may come from anywhere. Let us say call subscriber number 1 is trying to call to subscriber number 2. So, what subscriber number 1 it will do is that it will broadcast the signal over this line, this bus. Okay. So, there are n buses over here, and all these bus interface units, n bus interface units are hanging from or are connected to all the buses. So, each of the bus interface unit 1, 2, 3 up to n, they will receive that signal from n, but this bus interface unit 2 knows that this is supposed to be meant for me. So, he will allow this signal to get transferred to the output line, whereas others will not, will simply ignore it. Okay. So, this is again another fairly simple scheme. We have of course reduced the number of switching elements that are required. So, and it works, but it is not, once again using a bus etc. Will not be, I mean you will not get a very fast switch this way, but this works fairly well. If you want to go beyond this, that means you do not want so many lines etc. As I said that even if you have 1,000 subscribers you want to service from the same switch. So, even if a knockout switch you have 1,000 buses inside, okay, which not really is not feasible, okay, technically. So, we go to the other kind of switches which I showed earlier, namely multi-stage switches. And in multi-stage switches, actually this is one of the most commonly used switching architecture even today, so far as space division switches are concerned. So, in multi-stage switches we may actually provision less number of switching elements than are strictly required for the highest use, as we want to do, because we want to reduce the cost of the switch. All the lines can all the input lines can go to all the output lines, and it is broken up into several stages, as we will see. So, the advantages of a multi-stage switch is that it is reduced number of cross points, more than one path through the network. This increases reliability. If you remember that in our simple crossbar switch, if that one particular switch is bad, one particular pair of users cannot talk to each other. Okay. So, that is not really desirable. So, if since there are more than one path through the network, so even if one particular switching element becomes bad, they are still able to communicate. We will see. Of course, the control becomes more complex, and the other thing is that it may be blocking. Okay. So, as I said that in most of the cases it will not block, but in some cases it may be blocking. So, they have a large number of inlets and outlets which are sort of grouped into small groups, so that you can this problem with pins and input lines are not there, or even output lines. Often has identical switching building blocks forming a fabric. So, there are many switching building blocks consisting of some number of switches, and such modules are used all over the switch. Okay. As you can sort of might guess that in a multi-stage switch we will have different stages. So, the input will come from one side, then it will go to one stage, then maybe another stage, then maybe a third stage, and then maybe out. Okay. So, there are multiple stages, and each stage is broken up into small modules. Now, these modules can be identical, maybe, alright, and they may not be, or they may be identical. So, it is so that you can sort of easier to manufacture, cheaper to manufacture, etc., and then you can handle all your pins, etc., in this fashion. So, it often has identical switching building blocks forming a fabric, and fabric has multiple stages. So, this is just one example of a small multi-stage interconnection network. So, you have so this is, as you see, this is one stage. Okay, this is one stage, this is another stage, and this is the third stage. So, there are 3 stages over here, and each stage is broken up into small blocks. So, this is an 8 by 8 sort of switch, if you remember, if I have 8 by 8 switches in our crossbar switch, we require 64, or even if you take half of it, maybe 30 or about 30 switches. So, here each is a 2 by 2 switch. So, actually you can handle it with only one switch. So, you see the number of switches have come down drastically. Okay. But there are problems, as we will see, that it may be a blocking kind of system, we will see. So, now how do you know that something which is coming over from an input line, how does it reach the particular output line? Suppose the output lines are numbered, and since there are 8 output lines, we can code them using just 3 bits. So, from 000 to 111 we can code them in binary in this fashion. And this particular line which really is the input line number 011 wants to have a call to the line number, output line number 101. Now, if you know to which output line you want to go to, 1, 0 and 1, they really become control signals for this switches on the way. Say 1 means go to the lower output line, 0 means go to the upper output line. Okay. Since you can see that those which are starting with 0 come at the top, those which are starting with 1 come over here, and that is the same order, same binary number order that we are maintaining. If we maintain that, so and if we simply have the switch is simply a rule that if it looks at the bit, if it is 0 it connects to the upper line, and if it is 1 it connects to the lower line. So, 1 will connect it to the lower line, 0 will connect it to the upper line, 1 over in this switch will connect it to the lower line, and we will reach 101. So, this is almost self routing. Okay. It routes itself through the switching fabric. So, this entire thing is the switching fabric, and it can route itself. So, routing is easy. So, delta network is one kind of a multi-stage interconnection networks constructed of identical k by k switching elements, regular interconnection pattern suitable for large scale chip integration, self routing as we have shown requiring log k n, that means log n to the base k number of digits, and log n to the base so many is the same number of stages, each with n by k switching elements. All right. So, this is the picture that we had seen earlier. So, this is the diagram of a bigger delta network, maybe with 16 input lines and 16 output lines. Okay. As you can see that this is a 4 stage switch, because for 16 lines in order to code it you will require 4 bits. Okay. So, from 0000 up to 1111. So, if you require 4 bits, so you will require 4 stages as we have shown over here. Each bit decides whether that particular switch connects you to the upper line, upper output line or the lower output line, and from any of this input line there is a path to any of the other output line. Okay. So, this is a Banyan network, this is the 16 by 16 Banyan network. As you can see that in by doing it in this multi-stage fashion, once again, so in a regular crossbar switch, while you require something like 125 switching elements, here you require only say 8 into 4 32 switching elements. So, the number of switching elements is much less, but and there may be a problem of contention in a delta network. Of course, cells can be simultaneously switched through the network. However, cells may have to contend for same switching element. First we let us go back to the earlier diagram. You see as this fellow says 000 wants to talk to 0001. So, he will simply go like this, and similarly another line over here may want to go straight down to somewhere over here. So, so many calls can go through together, but this is not always the case. Okay. This is not always the case, as there may be contention for the same switching element, as we will see in this diagram. let us say sorry, okay, 0 1 1 0. So, 0 1 and then 1 sorry 0 0 will come here, then no, 0 will go straight, 0 1 1 0 and then 0 1 0 0. So, 0 upper 1 1 and you see that we have potentially we have got that for the same switching element from two different points in the network, it is sort of converging to the same switching element before it can proceed. So, there is going to be a contention over there once again. So, if there is a contention, obviously both of them cannot be handled at the same time. Okay. Either one of them has to wait, if we can make it wait somehow by putting it in some buffer or etc., or one of them will have to be blocked or dropped. Okay. So, although we save on the number of switching elements, sometimes we get a contention. Now, some ways to reduce contention is to provide buffers in every basic switching element, increase the internal link speed relative to the external speed, use backward feedback. So, these are different sort of techniques to reduce the contention. Okay. One is of course providing buffers, as I have already discussed. You could increase the internal link speed relative to the external speed. That means, if the internal link is much faster than the external speed at which you are pumping in, then both of them may be I mean you may be able to handle. So far as the input streams are concerned or the output streams are concerned, they will not notice the faster switching that is going on within the switch. So, they will think that there is no contention. Or use a backward feedback, that means at some later point in the min, if you find that there is a contention, then one of them you feed back so that it sort of recirculates. The other ways are to use multiple networks in parallel, okay. Provide multiple links internally between switching elements, shuffle cells first so that they do not collide later. Okay. This is also another kind of switch quite common, it is known as Batcher Banyan switch. Banyan part we have seen, Batcher part does some shuffling of the input cells so that in the Banyan part they do not collide by contending for the same switching element. The so in a space division switch, the big switch is broken into multi-stage smaller chunks. Okay. Another common type of space division switch I will show now is a 3-stage switch. Suppose I want an n by n switch. So, suppose if it were a crossbar, then it would be an n by n switch. This is replaced by n by n number of n into k switches in the first stage, followed by k number of n by n into n by n switches in the second stage, followed by n by n number of k into n switches in the third stage. So, let us take a first look at a simple example. So, this is a 3-stage switch. In the first stage, so we have 10 of them. So, our capital N is 10. So, first we put them into and our k is 2. So, we have 5 into 2 switches. So, we have 1, 2, 3, 4, 2 on the input stage. So, n by n that is 2 of them of 5 into 2 switches, and then 2 into 2 switches followed by 2 into 5 switches. So, let us say 5 wants to speak to 2. So, 5 comes here, gets switched in this fashion to 2, and 6 wants to talk to 1. So, 6 goes through this switching fabric in this fashion in the third stage, all right. So, for if you take now if you take the general case for n equal to 1000, small n equal to 50, k is equal to 10, this reduces the number of switches to 24,000 from about 500,000, okay, because if you have 1000 into 1000 divided by 2 is 500,000, that is the number of switching elements you would require for a simple crossbar kind of switch, whereas by breaking it up into 3 stages in this fashion, taking this particular value of small n and capital small k, namely 50 and 10, we reduce the number of switches to 24,000. However, the switch can handle only n star k by n. So, if n is 1000 and k is 10 and small n is 50, so n star k by n would be 200. Okay. So, only 200 simultaneous calls, so only 400 users can use it at the same time, which may once again, as I mentioned, that which may be fairly all right, okay, because you have a phone, but you are not talking on that phone all the time. Okay. Most of the time actually it is just lying idle, only some of the time you want to talk, and if the telephone company makes a good study and finds out that 400 is the maximum, I mean usually the kind of maximum number that is sufficient for a very low blocking probability even during busy hour, then that is fine, all right. So, this is the general scheme of this. You have small n lines feeding to each of these capital N by n modules of the first stage. So, you have a total of capital N lines, small n out of which is feeding to one module. So, you have small n into k kind of switches, so that this switch can direct it to any of the switches on this side. So, there are k of them here. There are capital N by n switch modules on this first stage, k modules in the second stage, and again capital N by n modules in the last stage, third stage. So, you have n by n plus k plus n by n this many modules. In a multi-stage interconnect network, we may either have a connection based kind of system, that means once a connection is made it is permanent till the call is held, as we have in an usual telephone network, or it may be cell by cell. That means although the user sort of goes on having the conversation, his stream of bits is divided into small cells and each cell is individually routed through the min. Many connections will need pass through more than one switch. So, cell based, that means routing tag, versus network based, which is routing tables. Okay. So, if you have tags it is faster, if it is table it is slightly slower, and as I said that static routing uses the same approach all the time, dynamic routing allows for change in routing depending on the traffic. So, what are tags? You remember that in a delta network we were putting that 0, 1 etc., we were encoding the input or the output, specifically the output lines, and then using that address to the cell can route itself through the network. So, that is an example of a tag, which means that within a switch each of the lines has got some kind of code in it, you might call it a tag, and then this tag will be used for routing. Now, if it is self routing like the one that is shown in delta network, which is very simple, it will be very fast. Okay. If it is some other kind of tag we are using where such a simple scheme does not hold, then maybe you will have to look up some table to find out, okay, this is where I want to go, all right. So, with tags cells can be augmented to include extra header information when they enter a switch. That means, you look at that which is the output line it wants to go to, and then add the code for that output line onto this cell, which sort of becomes the tag. For example, with the Siemens ATM chipset, each 53 byte octet or byte cell is augmented to a 64 byte cell as it enters the switch. So, these extra bytes are for putting in these tags, etc. This extra information speeds up the routing process. Now, in a connection based system, we discussed this earlier, but once again the path is determined once for the duration of the connection. That means, once the connection is made, for the entire duration of the connection the path remains the same. All cells of the connection follow the same path. Now, it may be a connection based system with cells. That means, once a connection is set up, a particular path is designated, that this is the path all the cells which are originating for this particular call will take. So, all cells of the connection follow the same path. This guarantees proper sequencing of cells. Of course, they will now go in order. Connection of course may be refused. That means, when you are trying to set up a connection, you find that in an intermediate stage there is not enough resource, okay, there is too much contention for that. So, the connection may be refused. Paths can be determined by a combination of random selection to distribute the load. You want to you see that if you remember that in a multistage switch specially, there are various paths from the input to the output. There are various possible paths. So, that if one path is not alright because of maybe some defect, or maybe one path is not very good because at that particular point of time that part is very loaded. So, you may route your path through some other part of the switch. And this what you might do is that you might do a random selection amongst the paths to distribute the load, careful selection to arrive at the correct destination. This selection can be done either centrally or in a step by step fashion, as is done in a delta network. So, we have different types of switching. You have connections plus tags, you have connectionless, which are tags. Of course, connectionless switches we will look at this in more detail when we discuss packet switches. So, the same discussion that we part of the discussion that we are having here would also be useful in the next lecture. So, we may have connectionless plus tags, we have connections plus tables. That means, if tags are not possible, you have to do some table lookup, because this table lookup will always be slightly costly in terms of time. Alright. So, the amount of the kind of speed that you can achieve with a table lookup becomes limited because of that. But anyway, this is again a possibility that you can have connections oriented system with using tables. You have connectionless systems using tables. This is also used in routers specially. Now, buffer, so we will look into buffers in more detail when we discuss packet switches, but buffers may be complete sharing between buffer. This is the best utilization of memory, best for bursts of equal loads. So, complete sharing means everybody can share all the, so there is a central memory kind of thing which is shared, alright. Or it may be complete partitioning. Naturally, complete partitioning would be faster and best for unbalanced load. Partial sharing, that means some of it may be centralized, some of it may be distributed, etc. So, buffer can be there may be various strategies regarding buffers. Next, we come to time division switches. Time division switches follow the almost the same principle as time division multiplexing, which is you remember about time division multiplexing, that the same line was being used for communication by different channels. What we did was that we kept a specific time slot for one channel, okay, and these time slots go in a round robin fashion. So, after a particular frame is over, that means all the input lines have had their time slots, then one particular channel will get back its second time slot and so on. So, it will go on in a round robin fashion. So, the same principle we use in time division switches. So, in time division switches the bits or bit streams may follow the same path. Okay. That means different calls are following the same path, but they are using different time slots. Okay. So, a fixed number of bits from each line is read into a RAM in order. This constitutes a single frame. That means, a fixed number of bits from each frame, each line. A mapping table reads from the RAM in a different order. For switching from line J to line K, the jth location is read in the kth step. This is shown here. Suppose these are the input lines 0, 1, 2, 3, 4, 5, 6, 7. The output is read in a somewhat different fashion 4, 7, 6, 3, 0, 5, 2, 1. That means, actually whatever the 0 the line 0 puts in this time slot would be read by line 4, because line 4 is reading in that time slot. So, 0 is line 0 is I mean in effect connected to line 4. Similarly, line 1 is connected to line 7. Line 3 is not connected to anybody, he is idle at the moment. So, 3 3. Similarly, 5 5. So, it is idle. Okay. And similarly, just as we have 0 4, we have 4 0. So, this is a bidirectional communication, duplex communication going on. So, in the first slot or the let us say the 0th slot, line number 4 reads it, and in the 4th time slot line number 0 reads it. So, line 0 is switched to line 4, 1 to 7 etc., and line 3 and 5 are idle. So, basic components of a TDM switch, I mean we will not have the time to go into the details of this. It has a dedicated internal buffer memory distinct from the RAM memory used for program code and data, and this buffer will sort of contain the bits which are to be written into and read, often on a completely separate physical module, that means printed writing card. Usually has at least 2 DMA bidirectional serial ports. If you have studied operating system, that is direct memory access, which is used for fast communication without the intervention of CPU. So, that is DMA, and of course, we want this as fast as possible. So, DMA bidirectional serial ports. Input and output are simultaneous on each port with dedicated hardware for each operation. So, our memories are very special, that means they have multiple port memories and serial IO on each port. So, this is a very simplified block diagram. Usually in your line the bit stream will come serially, but on the bus internally we want to put them together maybe 1 byte at a time. So, we have a serial to parallel converter for getting 8 bits and converting it to a byte, which will be fed in parallel. So, database it goes into the buffer RAM memory. There is a connection memory, which is that mapping table that we have talked about. So, when you are setting up a connection, you will make entries into the connection memory. We will just have a look. The connection memory is what we have already seen, and then it gets consecutive address generator is here, and then from the buffer memory once again it goes to the output side, and then there is a parallel to serial converter for feeding into the individual line. So, this is the data bus and this is the address bus. So, connection memory contains a list or table for mapping input time slots to output time slots. So, when a call is set up, you make entries in this connection memory. Pointer data values are set from the CPU on a per call basis. The data output of this memory is used as an address to access the buffer RAM. Decimal representation is shown. So, this is just if you show it. So, this is another example. So, in the address 0 we have pointer content is 14, that means line number 0 may be connecting to line number 14 in this example. Okay. Now, just one more thing, that assuming 1 byte is read from each line, each frame is to be processed in 125 microsecond. Remember how this 125 microsecond comes about? Remember we talked about the voice channel, and each voice channel requires a capacity of 64 kilobits per second, as we mentioned. So, 64 kilobits per second means that what is the gap between every bit? in 1 second there are 64,000 of them. So, it would be 64 kilobits per second if we handle 1 byte at a time. So, it will be 8 kilobytes per second, and 1 over 8 kilobytes per second would be 125 microsecond. So, this is the basic time for frame. Okay. And in the entire time division hierarchy, as we will see, time division multiplexing, this 125 microsecond is a very sacred figure. This is what everybody that sort of sticks to this figure, so that a voice call can smoothly fit into this. Of course, if you want to have a higher speed channel, then what you might do is in the same 125 microsecond slot you may pack in a large number of bits, that is all right, but we keep the frame size to be 125 microsecond. If memory cycle time is t microsecond and there are n lines, we have 2nt. Why 2? Because each of them have 2 operations, one read and one write. So, 2nt would be 125. So, a 1000 line switch will require a cycle time of about 60 nanosecond. Okay. That is the kind of memory speed, and as we will see, as the number of lines go up or as the speed of switches go up, this memory speed becomes a constraint. As with space division switches, it is possible to devise multi-stage switches. Now, just one last point about capacity allocation. I mentioned this, that the service providers actually want to provision less than the maximum possible. Okay. Now, but what would be the blocking probability if you provision it in a certain manner, let us say in the 3 stage switch. So, I will just give you the formula. If the average call arrival rate is say lambda calls per second, which is an exponential distribution as people have seen for voice network, for data network is different, we will come to that in the next lecture, and the average holding time is m seconds per call. So, which is Poisson distributed. The call load in Erlangs is A is equal to lambda m, this is called the load, and given a load A, we try to allocate a channel capacity n such that the call blocking probability B is at an acceptable level, typically around 1% or less. This is the typical figure that we try to achieve, that even with the in the busy hour we get not more than 1% call blocking probability, and the formula for calculating this is this: B is equal to a to the power n by n factorial into sigma of a to the power I by I factorial. Okay. So, you can use this formula or maybe write a small program to using this formula to calculate the call blocking probability given these values of A, N, I, etc. I of course is this thing. So, you can verify this. So, this is one last this thing, verify using Erlang B and Stirling's approximation for handling the factorial, that for large n, say 100, even with 70% average channel utilization, that is A by n, we get very small blocking probability. But of course, if the channel utilization or A by n becomes 80% and then 90%, what will happen is that you will find that your channel blocking probability is going up. Okay. And then you can do the same thing for a small n and try to see what happens. Thank you. Good day. So, in this lecture we will discuss about packet switches. That means packet switches are switches which are specifically designed for handling packets. We have seen the telecom switches like space division, time division switches, etc. Okay, we have also discussed something about multi-stage switches which are used quite often in packet switches also, but in this lecture we will specifically discuss about packet switches, which is at the heart of almost all your computer networks. Okay. So, first just to give you some motivation, that why do we require switches? The performance of a LAN can be considerably enhanced by moving over to switch LANs. Moving over from what? If you remember that some of the earliest kinds of LANs that we have just seen a brief glance of, some of them use shared memory like a hub or a bus, etc. Now, if you are using a shared medium, what is going to happen is that only two nodes connected to this LAN can communicate with each other at a particular point of time. Whereas, if you have a switch, multiple pairs of users or multiple pairs of nodes can communicate with each other at the same time. So, naturally you get a very good boost in performance of the overall LAN. So, that is one reason why we require switches. Of course, we require switches in other places also. Multiple distinct source destination pairs are able to communicate at the same time through a switch. So, that is why we require a switch in packet networks. A packet switch needs to look at the header of each packet to find the destination address of the packet. So, you do not have to do a full scale sort of lookup of a very big table. So, you have you look up only a very small table of VCI VPI in the VC table, replace but of course, virtual connections just as they are set up, they may be taken down. So, replace old VCI VPI with new ones, forward cell to outgoing interface, transmit cell onto link. So, this is the this is how an ATM switch works. So, if you you see that the basic concept of the cell remains the same. That means, we have some we have to find out the output port from the address, and here the address, once it is set up, after that the output the address is simply a small table of VCI VPI, which makes this lookup process much faster. So, this together with the fact that the cells are of same size, so you can develop your hardware in such a way, so that these ATM switches will work very fast. Otherwise, the rest of the switch and the switching principle remains the same as we have discussed already. Next comes the Ethernet switch, which is perhaps the most common type of switch that you see almost everywhere. As a matter of fact, this number of Ethernet switches which are being used and which are being put to use almost regularly is so high that the cost of these switches have also come down, you know, because if you produce something in very large number, you can amortize the cost of its development, etc., over a large number of switches. So, this cost of the switch comes down. So, Ethernet switches have become very cheap these days. Okay, a switch which used to cost maybe a lakh or so, maybe 10-15 years back, costs only a few thousand rupees today. So, this is the most common type of switch which we see everywhere.